Alright guys, I know I said yesterday we weren't going to do this, but I thought about it again, and I think it does make sense to talk about this for a little bit. I want to talk about how this, through some algebra, will eventually turn into this. Okay? But we have to use a little bit of convenient reorganizing using some properties of exponents that we have talked about maybe in the past. So I'm going to rewrite this as principal. Okay, now I'm going to go 1 plus r over n. But I'm going to raise that to the n divided by r. I'm going to close my bracket, and I'll raise that to the RT. Okay? And you might be thinking, you just completely changed the whole thing. It is no longer the same formula. Looks different, right? Okay? But think about this. Is this there? Is that a power raised to a power? What do you do with powers raised to powers? Multiply them. Is n over r times rt still nt? Okay, so these two things are still identical. They're the same thing. Okay, now the next thing I'm going to do is going to be a little bit creative, but it makes sense. Okay, and you can do this. Basically all I'm going to do here is redefine some terms. I'm going to let this exponent n over r, I'm going to call it m. Okay? So I can replace n over r with m, right? But if I do that, if n over r equals m, what is the reciprocal of n over r? R over n. Well, I got an r over n right there. What's the reciprocal of m then? 1 over m, isn't it? Okay, so that allows me to just redefine some stuff here. Should have a 1 in there. I've got my 1 plus now r over n. I've now called 1 over m. N over r, that exponent, I call m. I'm going to raise that to the RT. So that's exactly what we had. I just redefined things, right? Relabeled it. It's all now in terms of m. But let's think about what that looks like. This right here, now it's going to be a different letter that we're using, but this right here, that is exactly the same formula that Euler was looking at, or function that Euler was looking at right here. Isn't it? Okay, now we're using m's in ours instead of n. But what Euler came across is that as we get an m value or n value to be very, very big, this amount turned into e, right? Okay, and that's what we want to happen. Remember, we're compounding continuously. So back down in the thing that we're working on, okay, we want this m value, we want m to approach infinity because we're compounding continuously. Okay, because remember that's what this n right here, n right there was talking about the compounds. So we want that to compound continuously. We want this thing to tend to infinity with that m value. And if that happens, then what I have highlighted here that turns into e. So then rewriting things, p, the green stuff turns into e, still have my exponent of RT, and there's our continuously compound formula. Okay? But I wanted to show this because it shows you or demonstrates that our formulas that we have, okay, they don't just pop up from, somebody choosing a bunch of letters and numbers and throw them together and say it works, okay? There's reason, there's algebra behind it. So this is like if you're in like an advanced algebra class in college, okay? This is the type of algebra that you focus on. You do proofs like this, okay? Instead of maybe these types of questions. You might hit a couple of these, but a lot of those classes in college that are heavily algebra related are going to ask you to be able to do these types of things, okay? Which I think this stuff's more enjoyable than these specific problems, in my opinion. But does that kind of make sense, though? Okay. Doing an example over here again yesterday. I think we asked, I explained this in detail as we talked about it when class was over, but we didn't do the problem. But we discussed the idea that compounding continuously is always the best thing to do as a consumer, right? You always want the more the compounds, the more opportunity you have for increased revenue as the consumer. So this question here just says, it's using the same exact scenario that we did when we were compounding monthly or daily or whatever it may have been previously in section 4.1. But now it asks us to do it continuously. So they're going to say, A of t is equal to P e raised to RT. As I go through this, the principal is going to be $1,000. The interest rate is 12%, and the time period is going to be 3 years, okay? And basically what they're asking here at the end of this question is just compare your answers to the last calculation of the interest compounded at certain time periods. It's comparing what were you getting when you used this formula when n was maybe 1 to 12, 365, that kind of thing. Does that kind of make sense? Okay. So if we were to compare these things, let's use Desmos here. So if I use P times E to the RT, and I let P equal 1,000, R be 0.12, and T equal 3, we see there that we get 1433.32, right? If I go through with the formula that says P times 1 plus R divided by N, raised to the nt, let n equal 1, let p equal 1,000 again, let r be 0.12, and t is still 3. We see in that scenario that we have 1404. So compounding continuously here is greater than that amount right there, right? But here we only compound it one time, so let's compound it maybe at the end of each month. So I change that to 12. Change that to 12. 1430, it's greater than what it was when I compounded once, but it's still less than compounding continuously, right? If I change that to 365, type in the wrong spot, 365. It's a little bit closer, but this is still less, right? Okay, if I go 365 times 2, it's still less. Multiply that by maybe 12, so this would be doing it on the hour. Okay, that's still less. Okay, and we're going to find out that no matter what I make this number, compounding continuously is still going to be a greater revenue for me. So compounding continuously, hopefully that gives a visual that when they ask us, and you're seeing your homework questions, later on, they'll simply say, what is a better deal? Compounding a 6% interest continuously or compounding 6% interest daily? And there's not going to be any numbers. It's going to be two bubbles you get to choose, and if it's 6% for both situations, continuous is always the better option. Does that make sense? If everything else is static and the same, the continuous is best. Okay. They will then ask you questions that say, if I can give you 3% in continuous compounding, is that better or worse than giving you giving you like 3.2%, but only compound weekly? So in that situation, there are more things that are different. Okay, both percents are different, both interest rates are different, and the compounds are different. So there, you'd actually have to calculate, do some trial and error type things to determine which approach is best. Okay. Does anybody have questions on this? These two formulas, there's some questions on your final over these two concepts. I want to make sure that we are comfortable with them. If no questions, I'd like to go into 4.3 a little bit today. The next couple sections, they're probably all going to be kind of a, 4.3 introduces logarithms, and we're going to stick with logarithms through the end of our instruction until like Wednesday, and talk about all the different properties of logarithms, all the different things that we can do with them, and then hopefully by Wednesday, maybe late Tuesday, we can actually start seeing some applications of logarithms. Basically, what we're going to be able to do with a logarithm is, if we go back to one of these questions, let's say in like this situation right here, let's say that I want to have $3,000 in this account. I'm going to invest $1,000, and I know the bank is giving me a 12% interest rate. If I want to solve for t, if I want to know how, if I have $1,000 that is just sitting in my bank account, burning a hole in my pocket, whatever, and I want to invest it, and I want it to be turned into $3,000 eventually, because now $3,000, maybe I want to go buy, I don't know, some tools or something like that cost $3,000. I don't know, some object costs $3,000. I can run through the use of logarithms to help me determine the time in years that I need to wait till that turns into $3,000. Does that make sense? Right now, we don't know how to solve. We can't solve right now exponent or variables. Solve for variables that are in exponents. The logarithm allows us to do that. Okay, so that's where we're going to head today. So a logarithm, one thing I want to just make sure that we don't do to ourselves is when people see what we call transcendental expressions or equations, okay? Basically something that's non-polynomial, okay, is referred to as transcendental. They scare people because they got words in it. A lot of them have words in them like log, sine, cosine, tangent, those types of equations. They make people nervous because they look different than what we've ever dealt with. Okay? We treat them the same. They're still the same math and properties of all other objects that we've worked with in the past. So don't let the notation make you fearful and then just give up because it just looks scary. Does that make sense? So just make sure that you take that mindset. So every exponential function, f of x equals ax, with a being greater than 0 and not 1. We don't want a to be 1 because that's going to be a boring linear function. Says every exponential is a one-to-one function. First of all, we know it's a function. Every one of these blue curves, a to the x, okay, every one of them is going to pass the vertical line test. Okay? But because every exponential function is either always increasing, okay, this one is always increasing, right? Or always decreasing. That means they're monotonic. We'll talk about that previously. But because they are doing that, they are going to be able to pass the horizontal line test. And if they pass the horizontal line test, that allows them to be classified as one-to-one functions. Does anybody remember what one-to-one functions, why we want to recognize whether a function is one-to-one or not? Okay, so if it's one-to-one, then it has an inverse. And inverses undo each other, right? Like x squared and the square root of x. They will undo each other. So, exponentials have inverses. Their inverse is the logarithm. Okay? So that's what this is saying right here. The inverse function, f inverse, of an exponential is called the logarithmic function. It has base a, which is the same exact base as the exponential had. Okay? And we denote it with the word log. And then whatever that base is, we write it as a little subscript behind the word log. Okay? And this is simply what is the definition of inverses. It says f inverse of x equals y if and only if f of y equals x. And what that means to us, think about this. This is an input. Okay, so this is saying we have domain value of x, and this y here is saying you have a range of y. Right here, it's saying your domain is y, your input is y, your output or your range is x. Isn't that exactly what we've talked about with inverses? Is that if I have the point A comma B on f of x, then off f of inverse x we should have what? BA. So all this is the rule or the definition of what inverses do. Okay? An inverse, if f of x has domain A and range B, then f inverse has domain B and range A. We flip them. Okay? The definition of a logarithm says let A be a positive number with A cannot be 1. A cannot be 1 because A cannot be 1 with an exponential. Okay, so its inverse cannot have A equal 1 either. So the logarithmic function with base A is denoted by log base A, okay, or log subscript A. It's defined by this rule here. We call this, right here, the definition of a logarithm, okay? And people will ask, or you may ask, well, what is a logarithm? Do we know what a logarithm really is? If I were to classify it as something, as some other number, what is a logarithm? Think about this. This is saying the logarithm of base A of x, right? So the logarithm, this is, okay, the equal sign is the word is, right? So the logarithm base A of x is y. We'll come over here to the exponential. Isn't y, which is what this is, this here, is y. What is y right there? It's a exponent, isn't it? Okay. So a logarithm is an exponent that you raise a base to get some number x. Okay. So let me give you a specific scenario here. If I say log base 2 of 8, okay, that turns in to 3, okay, because 3 is the exponent that I raise the base 2 to get 8. What's 2 to the third? It's 8, okay, so this here is an exponent, and the exponent that it is 3. Does that make sense, everybody? Okay. Now this phrase here, this definition is, okay, that double arrow, if you remember, stands for the phrase if and only if, which we can also abbreviate as IFF. which means it's a two-way street. You can start with the logarithm side and change it to an exponential, or you can start with an exponential and change it to a logarithm. Okay? And we'll practice going back and forth between both of those. What you see in both formats here, you can see the location of where we put the base in the logarithmic format and where it transfers to in the exponential format, and you can see where the exponent goes in both those as well. Okay. One thing I like to do is, and even if I start with this side over here, I always like to have this, because the thing that I do, if I want to transfer this into a logarithmic form, I always go with this picture. I'll circle my base, and I'll draw an arrow that gets me across the equal sign. It gets me to my y. So I know I go a raised to my exponent of y. That gives me this side right there. Does that make sense? And then I'll draw an arrow that comes back that direction and gets me back across the equal sign. So now I'm transferring over the equal sign again. So I write my equal sign, and then whatever I am pointing to there in x. So it allows me, that little picture allows me to always take the logarithm and transfer into the exponential. Okay, and if I can do it that way, then it takes maybe a little bit longer, a little bit more thought to undo it. So if I have like 2 to the x equals like w, okay, well that is my, I know that that's my base, so when I write logarithm, that's my base, okay? This is my exponent, so that's actually going to be over here, and then I put w there. And if I write that, then what I'll do is, okay, if I go there to there, does that give me this side here? And then come back to w, does that give me that side? Does that kind of make sense? I'm just using arbitrary values of 2x and w. Those don't, there's no reason why I chose those. But that's how you go back and forth between exponential form and logarithmic form. There's going to be times where, like I said earlier, if I want to solve this equation here for t, right now this is an exponential form. So in order to solve for t, I need to change this into logarithmic form. Does that make sense? And there will be times where maybe I have an equation, I don't have any here right now, but there might be an equation that is in logarithmic form. In order to solve for the variable in logarithmic form, I need to change it to an exponent. So we need to be able to flop back and forth between those two things. It's much like if I had some of our equations that had x squared in them. To solve it, there's just x squared, there's no linear term. It's like x squared equals 144. Then to solve for x squared, I take the square root, right? Okay. If I have the square root of x is equal to 12, then to solve for x in that equation, don't I square both sides? So the idea is, because they're, in regards to solving equations that have exponentials, we need to be able to do the inverse. It's like adding, subtracting, or inverses, right? Multiplying, dividing. If I have 2x equals 5, okay, there's multiplication happening right here, right? So what operation do I need to solve for x? I need its inverse of division, right? Okay, so if I've got an equation here where I'm solving with exponentials, then in order to do that, I need its inverse to be able to do that. Okay, so that's kind of where we're going with this stuff. Here are some examples that we're going to run through that just kind of confirm the procedure that we're doing here. If I have log in logarithmic form, log base 10 of 100,000 is equal to 5. Okay. Well, what that means then is that if I take my base 10 and raise it to the 5th power, that should come back and give me 100,000. So that right there in logarithmic form provides that right there in exponential form. Does that make sense? And is 10 to the 5th 100,000? Okay, so the logarithm is the exponent that I raise the base to get the x value right there. Okay, so would you guys agree if I take 2 and raise it to the 3rd power, I can come back and get 8? Okay, if I take 2 and raise it to the negative third power, does that come back and give me 1/8? Well, 2 to the negative third can be rewritten as this, can it? And then 2 to the third is 8, so I can rewrite it that way. So 2 to the negative third does come back and give me 1/8. 5 to the r comes back and gives me s. That kind of makes sense to everybody? Okay, so that's how we go from logarithmic to exponential. A lot of times on your calculators, they all do what we need them to do, but sometimes you might have to do a couple extra things depending on the age of your calculator. Like the TI-83, 84s that are not like the plus or silvers or whatever, they don't have this option here. So like right here, I got 84 plus silver colored edition. So this is the newest one they make. So it's going to have the functions that I need. So if I want to go math and I go all the way down to option A, it says log base. So if I want to take the log of 8 with a base of 2, I can do that, and it's going to give me back 3. So it basically says 2 raised to the third gives me 8. Okay. This calculator actually has a mode. Right now I'm in what we call the classic mode. There's a math print mode, and this is happening on all your like gray or silver calculators should have this. If I hit second quit, now if I hit math and go down to option A, now you can see that it actually allows me to visualize 2 and 8 as my base. And 8, that thing that we put in the parentheses, and we're going to talk about this in trig as well. When we have a transcendental expression like this, the thing in parentheses is usually referred to as the argument. Okay? So 2 is my base, 8 is my argument. So what do I raise 2 to get back to 8? I get it's 3. Okay? The newer calculators have those abilities to change base. Your older calculators, like if you were to borrow, and I don't really have any that work right now, but if you were to borrow one of my 83 or 84s, they were like made in like 1998. Okay, so if I hit log on those, that's all that it allows me to see. Okay, it doesn't say log base, it just says log. And what this does is it says we're going to use only the base 10. Does that make sense? Okay. And they do that because it's the most common. You guys have heard the common log, right? That phrase before last year. Okay, it is. Our number system is base 10, correct? Okay, so that is one of the most utilized logarithms. So it's built in. That button is built in to have that base. So it's an understood base of 10 there. If I type in now like 100,000, it should give me back the 5 that we were talking about. Okay, but so what I'm trying to get at is sometimes your technology will not allow you to change the base. Okay, and if your technology does not allow you to change the base, there is a formula that we can go through, and we'll see it maybe in a couple days. It's called the change of base formula that will allow you to change the base to 10 of the particular log you're working with, so that you can utilize your calculator. Okay, however, things like Desmos, and I don't know where, I don't think it does it on this version of Desmos. This version of Desmos, all it lets me do is use log base 10. Okay, but if you go to the graphing version of Desmos, open your calculator down here at the bottom, go over to functions, go to miscellaneous, and then in the middle column, all the way at the bottom, it says log base A. There you can see when I type that in, it puts one of those boxes down here for me to actually put the base in. So I can put the base as 2, come over here, say 8, and you can see that generates 3. Does that make sense? I don't know. My hope is that maybe we don't even need the calculator as we go through this. And we learn the procedures, and we have the algebra background to be able to do this. But there's times where, let's say that I have, somebody give me a number. 7. So let's say, what do I raise 2 to get 7? Well, nobody off the top of their head is going to know that irrational number, correct? Okay, if I say what is 2 to the 8, everybody knows that's 3. Okay, but if I take 2 and raise it to now the 2.80735492206. Okay, a little bit of rounding there in that 6. That 6 must be a 5 in all actuality. But does that give me 7 back? Okay, so nobody would have known that. So in that case, you do have to use your calculator to produce that result for us. So that's just a little bit with where we can maybe use our calculators. Let's see what time we get out of here. 10 minutes? All right. So when we talk about logarithms being inverse to one another, that means that I should be able to take a of x and plug that into log base a of x for the variable x. And running through our algebra, we should just get x back. Okay? Inverses undo each other. So what we're doing here is saying that if I take my two functions, okay, f and f inverse, and I make them composite. This is the property right here that is true about inverses. Okay, let's go back maybe to let's say f inverse of x is x squared and f of x is square root of x. Okay, if I run through this with these functions here, okay, so f of x is my innermost function, so I'm gonna take that function and I'm gonna plug it into the x there. So that would give me radical x squared. Well, what's radical x squared? What's radical x times radical x? Just x. So we confirm that that's true, right? Okay. Or if I do this one, which is f inverse evaluated in f, so I'm going to take that and I'm going to plug it into that function. So that's going to look like this. Well, what's the square root of x squared? X. So it confirms that. And that's what happens when we have inverses, right? We should be able to plug one into the other and get x back. And it works both ways. So if one of our functions, f of x is a to the x, and the inverse is log base a of x, we should be able to go f inverse, which f inverse is this one right here, take that and replace it for x right there. And that's going to generate this thing right there. Does that make sense? Okay. And when I take a and I raise it to the log base a of x, it should generate x. Let's go back to this here. Give me well, we'll just use 2, cut this. Okay, so here I'm taking 2, which was my a, it's my base, raise it to the log with the same base. Does it end up giving me the x value back that is in that argument? So no matter what number I put here, if I put 71 there, I'm going to get back 71. Put 712, I get back 712. Now that's not the case if my bases are different. So if I have a base of 21, those are different. Okay, but if I have a base of 21 right here, they're going to be the same. So that's confirming that when I take f inverse and substitute it in for f, or into f, as a composite function, I should just get back x. Okay? This one, I think this route here is now taking this blue one, a of x, and plugging it into the x over here in the green one. And it gives this here. This, I think, is a little bit easier to think about. If I were to ask you in regards to what we know about logarithms already, what do I need to raise a to get a to the x? If I started with a, and I asked you, how do I get a to the x? What do I need to raise this to? What do I need to put right here so that turns into this? And you put x, right? Then that makes it a raised to the what Comes back and gives me a to the x. So that confirms that these two functions, a to the x and log base a of x, are indeed inverse to one another. Okay? If we do this, what do you guys remember about inverses in regards to the relationship in graphing? If I took like 2, so y equals 2 to the x. What should the logarithm be graphically in comparison to that? Like, what would it look like? How do I find it? Because remember what?
Once you take like the point 0 or something like that.
Okay, so 0, 1 is on there. So what else what's going to be on the other one then? 1, 0 will be on the inverse. Okay, is 1, 2 on that graph? So what should be on the other one? 2, 1. Is negative 1, 1/2 on that first one? So 1/2, negative 1 should be on the other one. And we can draw a smooth curve between those, right? Okay, so that smooth curve in this case is going to be log base 2 of x equals y. Okay, you guys remember that line right there? Y equals x. So when we want to graph a logarithm, what we end up doing, so if they gave me log base 2 of x equals y, what we're actually going to need to do is transform that into its exponential. Okay? So we will apply, so if I go if they say graph y equals log base 2 of x, what we will actually do is we'll say, okay, can't do that. Don't know how to do that. I'm going to take 2 raised to the y is equal to x. And now one of the things with creating inverses is that once we do this, once we apply the inverse property, we then switch the x's and y's. So I get that. So if I can graph 2x to the y, or 2 to the x equals y, and then use what Anthony was telling us about the ordered pairs switching, the domains and ranges switching spots, then that will give us the logarithm base 2 of x. Does that make sense? Which is identical to the reflection across the line y equals x. So 3 days ago, I told you we are going to need to make sure that we understand how to graph an exponential. Because if we can't graph an exponential, we are undoubtedly not going to be able to graph a logarithm, because you have to use the exponential graph to create the logarithmic graph. Okay? Unless you're some type of savant that just knows how to evaluate logarithmic functions in your head and find those ordered pairs right away. Does that make sense? Okay. Stop there. Tomorrow, I want to get into some properties that are basically these properties here, and there's going to be a handful more. You can memorize them. I don't even know them, to be honest with you, because I know the definition of a logarithm. And I know how to change it to an exponential. Think about this. But the reason these properties are here is because we see them so often that they say, if you can commit them to memory, it's going to be more efficient for you. I never do it, but if I go a, what can I raise a to? Any base, so that I get 1. It has to be 0. So like 2 to the 0 would give me 1. 10 to the 0 would give me 1, right? Okay? So if whenever you're working on a problem, if it says log base 5 of 1, you can now replace that with 0. Does that make sense? And make your equation, your problem a little bit easier. Same thing here in the second one. A raised to what power will give me A? A raised to the first gives me A. A raised to what power gives me A to the x? A to the x gives me A to the x. And then this one is actually starting with the exponential and working backwards to the logarithm. So we'll talk about, we don't have enough time to do that one, but we'll do that one tomorrow. But that's what we'll start with. Again, that's something I'll give you an option. If you want to memorize that, you can. But the reason this works is because log base A of x equals y, if and only if a to the y equals x. This last one is starting here and moving in that direction.